Hi everyone, I'm so glad to meet you all here in the GAGE Workshop for DAS. My name is Jonas Nora. Today I'm going to present our research that we work on, Research Institute of Innovative Technology for the Earth in Kyoto, Japan, entitled How Small Can You Detect with DAS? A case study in the Bōsō Peninsula. In this presentation, I would like to outline there are 6 key points that we are going to discuss. The first one, I'll begin with the reason why we detect earthquake using DAS. And then I'm going to show the field setting of our instrument that we have in Chiba, in Japan. And then the waveform response of DAS to natural earthquakes and how we detect the events, the spectral content, and the detectability dependence on azimuth. So the first question that we might ask is that the reason why we use DAS for studying earthquakes. Earthquake is an important subject that we are using to study the internal structure of the Earth. And the efforts that we have made so far is that almost all parts of the world on the surface has been covered by lots of sensors. But in some places where access is quite impossible to reach, for example, on the ocean, and in some places where we can see here the sensors are not there, it is because the cost of maintenance and the cost of installation is too, it's not too affordable. So we need a more affordable solution to cover this part of the world. So we are using DAS. DAS stands for Distributed Acoustic Sensing. It is a fiber optic cable instrument where we don't use discrete geophones or sensors, but we use the whole fiber optic as our sensors. So the benefit is that we will have a denser array of sensors along the fiber cable. Now, here's the field setting of our DAS in Chiba. In general, we have 2 wells. The first well is a 250-meter well, where we install 2 DAS, the straight cable and the helically wound cable. So there are 2 types of cable in this 250-meter well. And then the other well is the 880 meter, where we install another straight cable inside. And you see here, this is the diagram or the schematic of the wells. Here is the result of the waveform response of this 3 DAS instrument to natural earthquakes. You see here the difference among these 3 type of settings. And if you see more clearly, we can see that HVC, or the helically wound cable, provides less noisy data, but weaker amplitude response. And then the straight cables, so both STC and BC, so STC 250 is for the numbers here represent the depth of the well. So the straight cables provide stronger and clearer response. And you can see somewhere over here, this is the tube wave. And then this is the multiple wave, where in the BC, it shows less multiples. Here is the result of the P arrivals for these 3 settings. And then this is the S arrival for these 3 DAS instruments. So we are using the STA, LTA method and the STFT, or short time Fourier transform, to detect the event for these 3 DAS instruments. And then we also made a plot of waterfall plot to see the spectral content in our data. So if you see more clearly here, we can identify some noises For example, there is an interesting pattern here, the stripe pattern. So it turns out that this stripe pattern is the noise caused by the completion. So because some parts of the well has a poor cement integrity and the deeper part of the well has a better cement, so it turns out that in the poor quality of the cement, it will appear as this stripe pattern. And then there is a shallow noise here. This is because of the near surface noise. And we can see the four corner frequencies where here is the background noise and the PS arrival, and the completion noise is the highest noise in this data. And then one of the interesting thing is that here we have three events with magnitude 1.4, 1.3, and 0.8. The interesting thing is that here, if you see the 0.8 earthquake compared to the 1.4 magnitude, the 1.4 magnitude has smaller or weaker amplitude recorded than the smaller magnitude. So the question is why? If we see the figure on the right, you can see the azimuth of each events. So for event 3, this is the azimuth, and for event 6, this is the azimuth. So for this azimuth, it turns out that the amplitude appears weaker than this azimuth. So amplitude depends on azimuth, not only equidistance or depth or magnitude, but it clearly and strongly dependent on the azimuth, because the Earth is very heterogeneous. There is a crustal velocity heterogeneity and attenuation. So we have to focus when we would like to install our dust to study the earthquake. We have to also study the crustal velocity and the attenuation structure. So what we are getting here, the helically wound cable provides less noisy data but weaker amplitude response. And then the straight cables provide stronger and clearer response. It is significantly affected by cement integrity. So it turns out that the poor completion creates a kind of stripes pattern noise. And then the dust, we find that the dust is still able to detect earthquakes down to 0.8. So this is a really interesting finding. It is really able to detect earthquakes down to 0.8. So this is a really, really small earthquake. But we have to also concern that the detectability of dust depends on azimuth. So not merely based on the equidistance, magnitude, and depth, but it also depends on the azimuth. So that's all for my presentation. Thank you for attending. If you would like to contact or asking about some other details, you can reach me out in email or in LinkedIn. Thank you.